Welcome to the next video in a course in real analysis. This is lesson 4.1, indicating that these are just going to be exercises based off of the content of lesson 4. There will just be two short exercises, so this should be a pretty simple and a pretty quick video. And so here are the two exercises. Suppose that you have a poset and you have a chain of subsets. So A is a subset of B, B is a subset of the poset, and they are both non-empty and bounded above. Show that the suprema are in that order. Sup A precedes or preseeks sup B. Of course, there is a corresponding statement for the infima. Pay attention to the direction of the subsets and the inequality, but you should be encouraged to formulate that statement, right? The statement that corresponds to infima, and check your answer. You could Google it, but check that you're right about which direction the infima go in, and feel free to also give its proof if you want that exercise. Anyway, moving on to the next exercise. Again, we have a poset and a non-empty subset, and show that if the infimum is equal to the supremum, then the set must be a singleton. To begin the solution, and by the way, this is the solution, so if you don't want to see the solution, then please pause the video, set it aside, solve this problem for yourself, and then compare your solution against mine. But here's my solution. And so these sets are non-empty, bounded above, and therefore each of the suprema must exist. So that's just a nice thing to make sure that you get that kind of out of the way, that technically we have to check that. But anyway, now that we know that these suprema exist, let's just show that the supremum of B is an upper bound on the set A, right? Because if we can show that it is an upper bound, then it must follow that it preseeks the least upper bound. Remember, sup A, pretty much by definition, is the least upper bound. So if we show that it is one, right, if we show that sup B is one of the upper bounds, then it must be have sup A precede sup B. So all we have to do is show that sup B is an upper bound on the set A. Okay, but that's really trivial, right? Because if you take sup B, which is an upper bound on the set B, and you pick any element out of the set A, we'll immediately, right here, I guess I should write down a little bit, but it's very, very quick. So you should, I think you can fill this in, but let me maybe write a little bit down and say that if you pick an element, let's say, I'm just going to call it C, an element of A, then C must be an element of B, and then C is bounded above, right? That this upper bound sup B, we have C preseek sup B. And so this demonstrates that sup B is an upper bound on the set of all elements coming from the set A. Since it is an upper bound, then the inequality follows. So proof complete. Okay, for the second exercise, let us suppose for contradiction that we have some two distinct elements, and without loss of generality, if they're distinct, then one of them must strictly precede the other. One will assume that B precedes C. Well, since the infimum is a lower bound, then it must preseek the element B. Since since sup A is an upper bound, then it must be that C preceeks sup A. And in the middle, we have that B precedes C by assumption. Well, putting that together with transitivity of the precedes relation, it follows that inf A precedes sup A, and therefore they are not equal. But then we assumed that they were equal, so there's our contradiction, and the proof is complete. Finally, I'd like to end on an invitation to ask questions. So if you found anything in this video or related portions of the textbook confusing, please leave a question in the comments as clear as you can make it. And if I can address it in the comments, I will, but if it's more substantial, then I may make a video and include it in the playlist.